This special edition of CES Tech Talk is brought to you by ARM. ARM technology is at the heart of a computing and connectivity revolution, one that's transforming the way people live and businesses operate. ARM's advanced, energy-efficient processor designs have enabled intelligent computing in more than 150 billion chips, and its technologies now securely power products from the sensor to the smartphone and the car. Hey everybody, with the Consumer Technology Association, I'm Tyler Suiters. We are the owners and producers of CES, the world's largest, most influential tech event. And we're here to help you get CES ready. The show is January 7th through the 10th, 2020 in Las Vegas. And today we're talking about self-driving vehicles, a critical innovation for our health and welfare. Consider this, about 95% of car crashes in the U.S. today are caused by human error. So what happens if self-driving vehicles can fully eliminate human error from that equation? 37,000 people are killed in the U.S. in these kinds of accidents every year, and you move that out globally, we're talking about the potential to save more than 100 million lives worldwide. At CES, you will get ride and drive experiences and ride and no drive experiences. You can test technologies that support the future of self-driving vehicles, and that includes technologies that are evolving even as we speak. Parking assist, collision avoidance, emergency braking, much more. So today, a focus on self-driving vehicles. Not so much the cars themselves, but all that goes into making them smart, the artificial intelligence, the software involved. So a conversation with three different players in this field all at once, too. First of all, ARM. This is a company that's providing the IP for chips. That means delivering cloud services and providing a complete IoT solution. Remarkable innovation here. Also, NXP. This provides a clear, streamlined approach. It's a domain-based architecture, so we're talking about software and stack, etc. This is something that can intelligently group together the functions that allow cars to sense, to think, and to act very quickly. We're talking about managing complexity and separate concerns in almost real time, and often in real time. And finally, VSI Labs, a top advisor that supports R&D and planning departments, both in major auto companies and suppliers as well. It is technical and applied research across hardware, software, connectivity systems, all to advance SDV tech. So today, a deep dive brought to you by ARM into the world of self-driving vehicle innovation. For the special edition of CES Tech Talk, we are in the heart of the self-driving vehicle world, Silicon Valley, California, talking to three experts on this topic. Phil Magney is founder and principal advisor at VSI Labs. Mark Douglas is Field Software Solutions Architect at NXP. And Robert Day is Director of Automotive Solutions and Platforms at ARM. And gentlemen, pleasure to have you all with us today. Thank you.
It's a pleasure being here.
So this is a road trip for us. This is your hometown. Robert, let's start with you. We're looking ahead to the future of self-driving vehicles. What, how, and when? I mean, what will they look like on the road beyond what we're seeing today? And when do we reach, I don't know, I'll say critical mass, but maybe there's a better term for it.
Okay, so the first ones are going to look like regular cars, except they're going to be strewn with sensors and bits hanging off them. But the guts of the car are going to be very different. So, the mechanics that we as users use to actually, steer and press the brakes and accelerate, they're going to be the same. That's going to be based on a platform that's, well proven, is safe. The rest of it's all going to be compute and software. And that's where it gets really interesting.
So the parts we can't see.
The bits you can't see. Mm-hmm. So the sensors you can see. So you'll be able to see there's cameras, you'll be able to see there's LiDARs, you'll be able to see there's radars, and you'll know it's self-driving, but the bits that are actually doing all the real work, the heavy lifting, are going to be in the car.
Yeah, what's happening underneath all that is a competition for coulombs, for electricity. Yes. Because we're going to have a completely different thing on our hands, and we also have the evolution of electric vehicles as well. So we'll see a combination of these things being powered electrically, but also driven through a central computer or distributed compute. And we're seeing the evolution of those architectures at the same time. So there's a different kind of thing going on inside the vehicle that people aren't aware of, and they really don't need to be aware of. It's just going to work, and because a lot of people don't care how it gets done, just that it gets done.
But what is going to freak people out is there's not going to be a driver.
Yeah,
that's the bit that's going to really wind people up, because they can't see the compute. They can just see there's no driver. So.
I'd like to point out one other thing that's not very noticeable to looking at these cars is the fact that they all have one thing in common, and that's a by-wire architecture. So you have the ability to digitally actuate steering, throttle, and brake. This is something that is completely invisible, but it is the fundamental foundation from which an automated vehicle or automated vehicle technologies are built on.
Yeah.
And a lot of that's been there for the longest time. Even in your regular vehicles, you're shifting or you're doing something, you're not really moving anything mechanical. It's already sending senses, it's already actuating through, through different channels. It's not actually, you're not actually doing a shift. It's very interesting there.
So what's interesting is the guts that they can't see is basically a ton of different compute, with loads of software. And by loads, we're talking hundreds of millions of lines of software.
Yeah, just exponentially more than you're dealing with right now in a
Absolutely.
2020 car, say.
Absolutely.
So how difficult or how profound are those challenges? Not just the iteration, the evolution of, let's call it the hardware, but the body of the car, right? Making it more aerodynamic, more energy efficient, safer, all the things that go into constant vehicle development. But it's what you don't see. That's where I'd imagine from your world, that's where the challenges really lie.
Yeah, I think as Robert pointed out, you can certainly spot a development vehicle on the roads here in Silicon Valley because they do have massive arrays of sensors on the roof and highly exposed, a lot of bits and pieces hanging off, as Robert said. And if you got the pleasure of looking in the trunk, you would even be really taken aback because the things are loaded with computers and you have a massive power consumption going on with those things as well. That's the difference, I would say, where the gaps lie between today's development vehicles and future vehicles that are commercialized, is that stack, that hardware and software stack has to come down, be hardened, and put into a platform that is really feasible and practical.
Yeah, so if we could itemize those as, the safety elements, both in the hardware and the software, the power budget for the whole vehicle, and where all that's coming from. And
cue the eye roll if you can. If you're not joining us from the studio.
And
right?
head roll.
Yeah,
and head roll, I
head
know.
roll from Mark too.
I embellished that one. But those are like the things that when I go in to talk to customers, they're mainly either not aware of certain parts of that, but they are acutely aware of the power demands and what's going to happen and how much compute they have. Because what they started with in the POC, or the proof of concept, was, anything that they had available, a big PC, they ram it in the back of the vehicle, and then some AI accelerator component that's also super Coulomb hungry, and it's munching those things down. And where are they coming from? Well, they're driving in a traditional vehicle, and all that, when we go to manufacturing, which was a great kind of premise for a question, is all that has to be changed. All that whole paradigm has to change to lower power consumption, all of those things we talked about, being safe, being verifiable in the software and the hardware.
And likewise, I want to add too, Mark, to build on that, and the sensors. They're all highly exposed right now. They are very, very susceptible to inclement weather. In fact, these vehicles will not operate in inclement weather without solutions designed to accommodate, to keep those sensors clean and dry. And so you'll start seeing a tighter integration, more, various places within the vehicle hidden rather than being totally exposed like they are now.
Yeah, and Phil, coming from Minnesota, I'd assume that inclement weather has a different definition for you than
absolutely.
For us out
Yeah,
here.
we are probably the only company in the state of Minnesota that is developing automated vehicles. But we're not out to build a better self-driving car. We run a testing lab, and our job is to really test the different with our own development vehicles, test out different combinations of sensors and computers and software, and obviously a lot of the experiments we do are in the winter, so we are showing and demonstrating how you can operate these and cope with the inclement weather.
Robert, I want you to play, if you would, off of something that Mark said regarding the design and it all changing. And you were heading in this direction earlier, which is the way the car looks, not just on the outside, but really on the inside, because when you don't need to drive, why do you need 4 seats facing forward? Why do you need a cabin that has a specific design to it?
Yeah, and so it's very interesting. If you start positioning yourself from being a driver to a passenger, the inside of the car just changes completely. I actually don't want to know what speed we're doing. Okay, I kind of almost
It might
don't
become a mobile office, right?
Well, maybe, yeah. So I almost don't want to see what's going on around me. I'm just going to assume the car. So it's like being in an aeroplane. You're assuming that the pilot's going to get you there, and you really don't want to know what's kind of going on. And so I think in a self-driving car, there'll be all of these things in there which will enable us to be like in our home or in our office, enable us to keep working or keep playing or whatever we want to do. And it's almost a distraction from what's going on, kind of with what's going on in the car. So I don't think there's going to be beeps and buzzes and, so it's not like, KIT with Knight Rider where it says, okay, Michael, I'm going to take over now and off we go. It's really going to be, I'm just going to get you from A to B. And all you're going to do is, like with your Uber app, is you type in, I want to get downtown, and it will take you downtown. And it will say, you've arrived, get out.
Yeah, and far safer than we would ever do it ourselves.
Hell yeah.
Mark, Phil brought up an interesting term, one I hadn't heard before, hardening the stack. You
Yeah.
live, I believe, in the software stack.
Yeah, that's true.
Right?
Yeah. Oh, and the underlines too.
So-
The bootloaders, the kernel running underneath, and all of that
Well,
stuff.
give us a view of what
Sure.
your life is like right
Sure.
now. Not personally, but more about the professional space, because that's where you all are in consensus here.
Okay.
That's where the magic's happening.
Okay, let me
right
bring out a few, like the elephants in the room right now. Is not in this room, but in the actual, a virtual room, if you will, of what's going on. Is you have a sort of an evolution in the software realm where people have taken traditional operating systems like Linux and other POSIX type, sort of runtime code, and on top of that, they've layered stuff that needs to keep track of all these sensors, timestamp it, do it in a very quick fashion, and isolate that environment. And then you have maybe multiple application spaces that are going to kind of come up in the future. We're seeing the evolution of a software-defined vehicle right now. That's one elephant in the room. And then also this whole latency associated with time-stamping items and then comparing them and making sure you're not comparing stale data from one to the other. The other, I would say the other elephant in the room is there's a different POU, philosophy of use. There's a bit different POU that comes from different manufacturers, and you guys all interact with. I'm looking at the rest of the folks here that we all interact with people that have different ideas about it. Folks that are in areas with weather, they know they need LiDAR, radar, all the different types of sensors combined with camera. There's folks from another school of thought that believe that they can do the whole thing with just cameras and stereo cameras and changing different things. And we're starting to see that combined with the evolution of people trying to make the neural nets learn and be more accurate with less information, or train them in a different fashion. So there's a whole bunch of different things that feed into this system to make it more efficient and better and so on. So I just threw out a whole bunch of stuff that the guys can work with if they want to. But
I'll just add, based on the use cases, it's something that I like to always point out. When you're talking about automated vehicle technologies or driverless technologies, whatever label you want to call that, you really have to look at the different use cases, and they're kind of some primary ones. Like, for example, you have series production automated technologies now coming into the market, level 2, level 2 plus, eventually level 3. And so that's one trajectory, and OEMs and developers are often working on that path by itself, because that's so unique, And then you have the other companies working on the robo-taxis, which are, of course, your level 4 vehicles, and those are the ones we were talking about earlier, fantasizing about having the, everything in the interior, being able to, do what you want to do, and so
Not
forth.
fantasizing, envisioning.
Exactly. And then, of course, you have low-speed shuttles, which are now a very pragmatic use case for automated vehicles that operate in campuses or communities or low-speed operating kind of people movers. So you got to kind of take a look at the different trajectories of it to really understand what's going on.
Yeah. So I'd like to kind of come back to your initial question of when, how, what, where.
Yeah, that's an open-ended question, Robert. So you can hit
all right.
that anytime.
We'll keep going on that. So one of the interesting things that's coming off what something Phil just said is, what these initial deployments are going to look like is they're going to be very specific use cases or operational design domains, ODDs they're called. And it's going to be, well, I'm going to be in this part of the city. I'm going to go at this speed. I'm only going to go out when it's daytime, only in this weather. And that defines how the car is going to operate. Then what you can do is you can kind of laser in on, well, if I know I'm only going to be here, I'm going to map the heck out of it. I'm going to have these sort of sensors. I'm going to know where I am at any one time. Okay, and I can update that information just because I've got a very specific place I'm going to go. And so that will enable these first self-driving cars to actually hit the roads and hit the roads without having the safety driver. And the safety driver is the bit right now which is basically making sure that these things operate correctly because they can take over at any time.
Highly constrained operating design domain, I completely agree with that. I think it'll even be, it might even go further than that. It might be specific roads, specific lanes, specific times a day. You might even have predetermined drop-off and pickup points. I mean, the whole idea here is to limit the exposure of that vehicle to so-called edge cases or things that are outside of your control.
Well, humans.
I was going to say humans making poor decisions, right? Yeah.
But there'll be plenty of redundancy in there. I mean, there'll be plenty of safety checkers in there. There'll be traditional elements always, looking and grabbing and tapping off of the instructions that go to the drive-by-wire system. Because if you're going around a turn at 30 miles an hour and the whole system says you should accelerate, depending on the weather and stuff and what you're, measuring with the inertial systems and such, you're not going to want to do that, and something needs to catch that, and that'll always be there. In fact, a lot of the designs right now, they don't worry so much about the safety of the whole system because they have a checker that's at an ASIL level that's actually checking. So a lot of people that when we come in on and talk to them, they're not yet transitioning in their brains. They're starting to a little bit that they need a certain amount of that in the main system, but they're going, we don't worry about that yet because we've got something always watchdogging and taking a look at that.
So, Mark, is this a deterministic wrapper then, basically the checker that essentially says, okay, there are certain things we physically can and cannot do under certain conditions, basically?
That's
and
right.
I think there have been several companies that have talked about their own checker solutions, if you will. I won't get into names, but
Yeah, it almost sounds like, and this is probably a ham-handed way to put it, but like geofencing.
Yes,
There's
it's exactly
certain things
geofencing.
Boy, thanks for the validation, Rob.
Welcome.
Wow.
Yeah, you can bring
You
those
got it
terms
in
out.
one.
So, Mark, you touched on the idea of responsibility, the redundancy
Yes.
of having a backup driver.
Yes.
Another point that comes to mind that you took a step in this direction, but responsiveness. And for the last 50 years, we talk about cars and responsiveness. You're talking about a sports car and how
right.
quickly it can corner, how well it moves.
Oh,
right?
and
How
those are
nimble
the
it
things that we like to drive. We like to do. This whole thing is going to be very jarring because we're talking about we're taking that element away from folks, and they're going to be driving, for their own enjoyable pleasure rather than between these other reasons. But anyway, sorry.
That's okay. That responsiveness, though, is very much in your court from a software point of view because this is the exceptionally low latency you have. The responsiveness meaning the incoming data, and then the reaction of the vehicle.
Yeah, let's give you some perspective too. Like they say, race car drivers react at. I've seen all this data between 350 to 400 milliseconds, and normal schmoes and people like us, we maybe we're at half a second or 500 milliseconds. And a lot of times when we try to enter these designs at different stages, we find that the perception element and the planning element are the long poles in the tent in the software stand. From a software standpoint, those need to be sub 25 milliseconds, 50. So when they concatenate together, the whole trip should be under 100 or 150 milliseconds. Because that comes back to that, so that's the latency perspective that, we want to lend to this thing, which is, a little bit more low level is you've got to process all that in that certain amount of time period. And that's well under what we do. And of course, if that can happen, then the result of a ball rolling out into the street or a young child, God forbid, flying out into the road, you've got a lot more reaction time to do something with that, and hence stopping distance and a lot of different things that Robert.
Yeah. So one of the challenges there is we've got all these sensors. You've got HD cameras, you've got LiDAR, you've got radar. It's pumping all of these pipes into the car. So you have to get that data to the compute, then you have to make sense of it, or you have to process it.
Right.
You have to make sense of it, and then you have to decide what to do, all in that time frame.
Yep.
So
And
just
there's a-
think how much compute's needed
Well, there's one
to do
element.
that.
There's one element that's receiving all of that.
Yeah, absolutely.
And so, do you have multiple elements receiving it, and then compare the answer?
Yeah.
You know, a lot of people are doing things like that. You know, so
And it has to stitch it all together in real time and do it like, 20, 30, 40 times a second.
Yeah.
That's right.
Yeah, so it's very interesting because, the sensors are not just looking forward. As we as humans typically look forward until we have to do a maneuver. They're looking all around because they have to get the environment that's all around the car. So they're looking not just for, stuff that we're going to do, the car's going to do, but what's happening around it. And therefore can sort of take evasive action if necessary.
Yeah, for example, like, some of the level 2+ features that are being pushed out right now, like in the Tesla vehicles, where you can overtake slower vehicles, and so the vehicle will automatically change lanes.
Yeah.
And of course, to do that, you need a lot of intelligence. You need to be absolutely certain that there's nobody coming from behind at a high rate of speed.
Yeah.
Of course, that's a very camera-centric solution, and they're good at it. I'll give them credit. I mean, they frankly are one of the best at automated vehicle technologies and doing it with a camera. But yeah, the level of intelligence and of course the level of safety just rises considerably once you go to the more advanced levels of
and
function.
that safety has to go all the way through. So, you have to know that the stuff you're getting from the sensors is correct. Okay. You have to process it correctly. You have to make the right decision about what it is correctly, and then make the right decision on what to do correctly.
and since it's temporal, everything cascades, right? So everything is dependent on the other one. So every part or every subsystem has to be at a certain safe level or verified level. That way, that the data that's coming in, is makes sense, and then there's also that checker at the end to make sure that there's something.
But so I want to come back to something Phil said as well. It's like, all of the autonomous prototypes out there right now, self-driving car prototypes, you look in the trunk and it's all full of compute. And it's literally, so it's not deployable. It's too hot, it's too big, it's too heavy, it's too power consumptive, it's too everything.
Is it prototype? Is that the right term?
Prototype, I think, is the right term right
Yeah,
now. Because what this is really doing is this car is testing the sensors and the software and make sure that they can do the right thing. It's everything we just talked about. So they're throwing compute at it. It's like, I don't know how much compute I need. I'm just going to stick a trunk full of compute. And that might sound a little bit flippant, but it's sort of what we see on a day-to-day basis. But that's not deployable. Because if I get in a robo-taxi and I go to put my bag in the back, then there's a ton of compute, and the car's super hot because of all the compute. It's like, no, that's not practical. So what we're looking at now, as an industry generally, but we specifically as ARM, is how can we reduce everything, the size, the power, keep the performance, reduce the thermals and everything else. And luckily ARM's really quite good at that because we're in the small things you carry around in your pocket every day with a lot of compute in it.
Is the process parallel to or somewhat similar to the evolution of EVs, electric vehicles, in that when you were, Robert, talking about a prototype and you've got compute throughout the whole car, I'm thinking back to the first, maybe not the first, but the evolution of EVs and how you just loaded up a car with as many batteries as it could hold, right? Because they couldn't get small enough or powerful enough. And you didn't worry about luggage, where people would sit, or how hot it got. It was just about what can we do to generate that
that is
electricity.
an interesting analogy, actually, because
Powertrain is probably outside of our scope, right?
Yeah.
I don't know, maybe Mark, you've had some experience in powertrain, but
No, only in the management of what I
Sure.
see the evolution,
Sure.
where everything is going to be reporting up to a central system
Exactly.
and managing it. But
Yeah.
that's the software-defined vehicle,
Exactly.
which is a generation or two above what we're talking
But
about.
but it's the complexity is so high in this. You're not just optimizing battery technology. You're optimizing software. You're optimizing where do you stick the compute. There's this whole thing right now is, do you have one big central brain like a human that's taking all this input, and I'm waving my hands there, taking all this input and then processing it like a human brain does? Or do you actually start putting intelligence towards where the sensors are? And so each sensor becomes intelligent. So the compute just goes, oh, I only need to worry about this sensor because all the rest of them have said, there's nothing out there, don't worry.
Well, where do you all lie on that?
there's
One versus
there's
another.
different schools of thought. I mean, at
There
one
are,
end of the
yeah.
spectrum, you say, okay, let's take all the raw data we can get.
Yes.
And then put it in the central compute and try to make sense of it that way. The other school of thought is let's take intelligent sensors that can produce object data
Yeah.
and work with that. And typically, I would say, as far as prototype vehicles, it's a combination of things. I mean,
It's mainly central compute right now, and I think it's because then the people developing the autonomous system kind of own all of it. It's like if I'm not sure I'm ready to trust that distributed sensor telling me something, whereas if I'm just getting feeds that are just raw feeds, I trust that everything I do with my software and my hardware. So, but I think now they're looking towards deployment. It's different. It's like, okay, I can't just deploy this trunk full of compute. I'm going to have to, optimize here.
Yeah, that's
so
why
that's what I think, Phil. I mean, just
yeah, I would completely agree.
Yeah, that's why complementary software for optimizing the training of the neural nets and the accuracy of them will prevail, I think, in the long run, because then you can put lower quality cameras, you can put 3 or 4 cameras in different areas and do different things, and then always select which one or compare the answers of those things as they come in. I think the one thing that we're seeing folks do is they're putting enough sensors on those vehicles for that there's 2 different markets now too. There's the level 2 plus that we were talking about, Phil was talking about, and then there's the other case, and they don't necessarily scale. You couldn't build one and have it go into the full autonomy scale or you couldn't do something inexpensive with full autonomy and bring it into the lower end. That's my feeling there. But I think a lot of times people will put enough sensors so that way you can drive the vehicle with half the compute and so on. So
yeah.
And some sensors too, you're getting some innovation, a lot of innovation actually in the sensor space, where they're coupling a couple of different sensors in one module. So naturally they apply some processing and some software there to totally synchronize that and filter out the junk and give you a much better data that you can build into your environmental model. So,
I think we're seeing that with some of the level 2 stuff right now, with the cameras and radar being combined. So
yeah,
you
solid
get this
state
sense
lidar
of what do we
with multiple cameras, and that is going to come in one particular chassis, one particular sensor, and that can be placed, and so you get a very rich perception, a very believable, you would think, perception result, and that's usually the ID of the vehicle, the tracking of the vehicle, the vector, the direction that's going, the rate, and then there's a prediction element based on what it's doing. So we can see that in a lot of the typical.
And the other thing is, as you distribute, as you go out towards the sensor edge, as we call it, then you have to get the size down, you have to get the power down, you have to get the cost down. Okay, and so that whole economy of, well, I'm moving some of the compute around, but I have to make it a lot smaller, a lot more power efficient, because it's going out towards where the sensor is.
So this is just one area, right, of central versus distributed. If we could back out to go macro for a moment, how many different topics of conversation are there where there are various schools of thought across a self-driving vehicle right now about the elements that make it? Almost polar opposites in terms of how you get to the same place, very different directions.
Well, central domain computing has been a topic, it's been talked about for probably 10, 15 years. The auto industry has moved very, very slow toward that, right? But they're beginning to see and recognize the benefits of that central compute architecture. The one OEM that really came in and did it totally different, and obviously that's Tesla. That is, in my opinion, that is a proxy for future vehicle architecture because it is truly a software-defined car. And I think that is, honestly, the direction that a lot of OEMs are going with respect to their architecture. How long it'll take them to get there, I don't know, because they're up against 100 years of doing things the old way, and that is a highly distributed system where you've got all this logic distributed and pushed out rather than centrally managed like Tesla does.
Yeah, well, that's a disruptive OEM, right? Yep. That's not a traditional Ford, GM kind of local, been around forever and they're evolving, but that's very different. We have other guys on the scene, Rivian, other folks as well that are doing. But I always feel like every time I go in to talk to somebody with whatever they're doing, I got to establish a lexicon of some sort. Like, what do they mean when they say this?
It's not common, Mark.
No, it's not. Right? Yeah, and nobody shares it. And you don't really understand, and like, I don't really know that Tesla has a software-defined vehicle. I just know that a lot of people are looking around. They're seeing the compute. They're seeing these extra cycles. They want to add other features to those cycles. And then, of course, there's this, I think we're going to see the same phenomenon we saw in the networking space, which was which when we evolved to software-defined networking, is this consolidation. I don't know if it's in one SoC or multiple SoCs, but I think there's going to be a force of that, and what'll start coming out is virtual machines and different things that need to provide protection and all that kind of stuff. So everybody's probably going to evolve in the way that they where their lineage is, where they're coming from. I don't know that maybe there'll be people or developers that'll start fresh. But I don't know.
Well, sorry.
I was just going to just quickly, and then I'll let you jump on that one. But I was going to say that one of the things the OEMs really would like to be able to do is this remote feature enablement. So you configure the cars the same, they're built the same to the same specs, the vehicles hit the showrooms and then they get in the customer hands, and then the feature enablement is done over the air with software. And so you pay the extra $5,000 or whatever they're asking these days for full self-driving, and then they push it out to you, and then you have it.
And that's the aftermarket of the future.
Well, I don't know if I would label it the aftermarket. That is something now that is highly vertically integrated. I mean, you really, I don't know where we'll be 50 years from now or 100 years from now if the aftermarket is actually going to be able to get down into the ECUs. It's kind of a scary proposition, but no, the ability to enable new features and options remotely via software. So.
Yeah. So that's a really good point. It's like, well, if I need an extra, 100 horsepower, oh, that's a software tweak. We can do that.
That's a
which is scary.
So my brain is thinking this whole thing, like what Phil just opened up, is like, yeah, we knew it was there, and we didn't really talk about it. There's another elephant in the room. But, okay, so I got a whole new set of code going down. I got to bring that in. I got to not let it touch. It's got to stay contained. It's got to be in its own sandbox. I got to boot it up on some additional. This is where when I'm talking about VMs being available on the SoCs. Boot it up in there, test it, run some tests, and then say, okay, now it's deployable. And then when does that get deployed? Is it when I shut the vehicle down and then it gets deployed and then fired up and then it's tested throughout that process and then I start driving it, or do I, so there's a huge. I see it in my head that all these a containment of the domain, and then all that stuff. And then there's folks that when they drive throughout the road, they're throughout wherever they're at, with all the sensors are collecting this data. People want that data, and they want to get it up to the cloud, and then so there's both directions. They want to get it up to the cloud and then share it and then enhance other things. There's a lot of other potential there. There's law enforcement potential. There's a whole bunch of different things. Advertising. And that data is coming back up from the sensors that were on the vehicle that were recording as they drove down the road. So, you know what I mean? So it gets kind of mind-boggling.
And the other elephant in the room is then who owns the data?
Yeah, exactly.
And can they sell it? Yeah.
Pause there. It's a separate podcast called 4.
That's right. So one of the things that's really interesting. Sorry, I'm if that's all right. Yeah, sure. Okay. Is the difference between ADAS, which is level 2 and a bit of level 2 plus, and autonomous. Okay, the difference is so huge that there's not one company's really going to be able to do autonomy. Okay?
Completely different market.
Absolutely.
That
So
has to be
the traditional
understood.
automakers, the OEMs and the tier ones can do ADAS. Okay, they can get there. They've proven it. It's in our cars. So we have emergency automatic braking, all that sort of stuff. Autonomous is just too big. And so what's happening now is we're seeing relationships, we're seeing people starting to work together. And these are people that don't traditionally work together and now saying, yeah, this is a bit too big. So the autonomous technology providers are working with the OEMs. The tier ones are coming in. Everybody's trying to figure out, how do we actually do this and get this to deployment? You've been doing your prototyping. Everybody's saying we're still a way off when we're actually going to deploy this. How do we get there? And we're starting to see a lot more kind of consortiums being formed. We're seeing a lot more kind of interest in partnering and working together as an industry. And that's a real shift in the auto industry.
Ecosystem management is obviously a key term now. Everybody is talking about who's within their ecosystem and who are their partners and so forth.
Robert, I don't want to lose track of this point that ARM has a heavy presence at CES 2020. How much can you tell us about what you all have planned for the show and the meetings and the engagement and what you'll do at the center of the tech universe during the show?
So CES is a very busy show for ARM. If you think about consumer electronics generally, Well, that's ARM's sweet spot. So most of what you will see in most of the halls is somehow powered by ARM. When it gets to automotive, it's interesting because the automotive presence at CES has grown dramatically, but it's not always obvious where ARM is in a car. And so what we typically do as ARM is we kind of produce an automotive kind of guide to what's interesting to see on the show floor with ARM tech in it. So we will have booklets at the show that you can come and pick one up that will basically give you a guide to all the fun, cool stuff that's actually powered by ARM devices in automotive. And it's amazing the different types of systems, from infotainment to autonomous systems to just everything that's going on that's cool at CES powered by ARM. Yeah,
completely agree.
Great launching point for a final lap. All right, I'd like to give each of you one sentence. It can be a run-on sentence, and I'm going to give you a time frame. So let's bring it back to almost where we started here. Phil, for you, one sentence on where the industry will be 5 years from now.
Okay, 5 years from now, I think we will see a lot more on the ADAS side. A lot more of the incremental automation and active and advanced safety features brought out to series production cars, because frankly, in my opinion, you are going to see, this business is not going to change overnight, and you are going to see series production cars sold as they've been for the last, dozens of years for the next, 10 or 20 years. It's going to be a while before that starts to fall off. So in 5 years, I would say, we're going to see a lot more in series production, but then we'll be a lot further ahead in terms of the level 4 stuff, and there'll be some deployments in some parts of the country on a very limited basis.
All right. Mark, let's double that time frame.
Follow
a
the
decade
money.
from now.
Follow the money on any of these questions. Because right now what I'm seeing is, and I was really excited about, I still am excited, but about a year ago, everybody was doing these things, and now people are trying to enhance them. But I'd say between 5, 10, and beyond, if you look at where the money is, where things are going, it's still in ADAS. It's still level 2, level 3. I don't see a huge mad dash to get to where people were predicting full autonomy would have been in 2025. It's getting bumped out. I'm hearing numbers like 2030 and so on. And I don't see the investment. I see the investment again, there's two markets here. There's the safety, and there's the level 2 plus kind of stuff, and people creep it into level 3, and people have opinions about that. But then the full autonomy, it will be sandboxed. It'll be somewhere around with a lot of parameters. I just kind of I don't see a mad dash to that, because I don't see the volumes. Typically, don't see the volumes in that at the traditional level. So I just see our current vehicles getting much smarter as they move along.
Right.
And maybe there'll be a point where that chasm will be crossed. I bring that old term up, but that's I don't know. Boy, when you asked Phil that question, I was like, wow, I'm glad you asked him first, because then I thought, follow the money. You got to follow the money.
Yeah.
Because a lot of this stuff is great, and we can get all this technology and try to ram it into something, but it's how practical is it going to be, and where is it going to result in?
Right. So, Robert, final to you. 25 years from now, it's 2035. No, 2045.
2045.
Working on my math very quickly.
Yeah, no, that's good.
2045.
I'll have a
2045.
walker then. I don't know about you. I may not even be.
Well, yeah.
But you can go anywhere you want, Mark.
So, that's right. So an autonomous car will pick Mark up every day. That's for sure.
If he's still alive.
That's right. If he's still alive. So I think what will have happened by then is car ownership will have changed. We will not own our own cars anymore, or at least if we do, they'll be hobby cars. Okay. Ride sharing will be an interesting thing, whether it's dominated by the current ride sharing companies, or whether we all do our own kind of micro ride sharing, in that I'm going to buy a car, but then I'm going to share it with everyone else, or I'm just going to share somebody else's car. So basically, our whole model for car ownership and how we use cars, whether we're self-driving or not self-driving, is going to change. But I think there will be, people will actually start to see the benefits of having cars making decisions versus humans on the road. And I think at that point, 25 years from now, we could well see more self-driving cars than driven cars on the road.
And much safer roads, highways,
yes.
streets.
Yes, yeah. You can comb your hair and eat without crashing.
Legally, yes.
Yes.
What a conversation. Robert Day, is Director of Automotive Solutions and Platforms at ARM. Mark Douglas is Field Software Solutions Architect at NXP. And Phil Magney is Founder and Principal Advisor at VSI Labs. Gentlemen, I feel like I'm flipping on the lights right before closing time and killing a great conversation, but what a blast today. Thank you all for the time.
Thank you.
It's our pleasure. Thank you.
Absolutely.
All right, coming up on our next edition of CES Tech Talk, a very hot topic here in Washington for various reasons, but really one that's happening around the world. A look at cryptocurrency. That is on our next edition of CES Tech Talk. We are here to help you get CES ready, so do yourself a favor, subscribe to this CES Tech Talk podcast. That way you won't miss a single episode as you're getting ready for the next show. Speaking of, CES 2020 is January 7th through the 10th in Las Vegas. The information you need to prep yourself and your trip is at ces.tech. As always, none of this is even remotely possible without the true stars of our podcast, executive producer Tina Anthony and our senior studio engineer, John Lindsay. Y'all are the best in the business. I'm Tyler Suiters. Let's talk tech again soon.